Hey guys, welcome back to Code Streak Daily. In today's video, we are going to solve lead codes problem, and the problem is of a hard difficulty. It's very hard, and we have the title height of a binary tree after subtree removal queries. So don't worry, we'll break down the solution into simple, easy to understand steps. Okay. The problem gives us a binary tree with the nodes labeled uniquely from 1 to n. Okay. So now let's see. You are given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n. You're also given an array queries of size m. You have to perform m independent queries on the tree where the ith query you do the following. We have to remove the subtree rooted at the node with the value queries I from the tree. It is guaranteed that queries I will not be equal to the value of the root. Return an array answer of size m where answer of I is the height of the tree after performing the ith query. We do have a note here. The queries are independent, so the tree returns to its initial state after each query. The height of tree is the number of edges in the longest simple path from the root to some node in the tree. Okay, so here we have a tree here with the nodes 1, 3, 4, 2, and there is null 6, 5, and null 7. So here these nulls represent here 1, 3, 4, and 2. There is null here 6, 5. Here null and null, null and null, null and 7. We have queries 4. The output will be 2. Okay. The diagram above shows the tree after removing the subtree rooted at node with value 4. The height of the tree is 2, 1, 3 and 2. So here we have the node queries is given as node 4. So we have to remove this particular node and the subtree which is associated with it. So this is the complete tree, and the subtree which is associated with the node 4 is 6, 5 and 7. This subtree contains the node 6, 5 and 7. So when we remove this node, all these nodes will also be removed. Therefore the left tree is only with 1, 3 and 2. So basically you consider this as a whole tree, and this is one of the branch. When you cut the branch, all the small leaves and everything of a branch will also be cut down, right? So assume like that. And here we have another example with the nodes 5, 8, 2, 1, 3, 7, 4, 6. There are queries 3, 4, 2, 8. So we do have to remove 3, 2, 4 and 8. Okay, so we have the following queries. Removing the subtree rooted at node with value 3, the height of the tree becomes 3. When we remove this, we'll be left with 5, 8, 2, 4. This is the height, right? Removing the subtree rooted with node value 2. When we remove this value, we will be left with 5, 8 and 1. Then we have to remove the root at node with value 4. As it is already removed, sorry, we are going to remove that. Then we will have 5, 8, 2 and 6. Then we have to remove the subtree rooted at node with value 8. This one. Then we will be left with 5 and 9 and 3. Okay. So now we have to return the height of the tree after each query. That's it. Okay. Now let's see how to solve this problem here. To solve this problem efficiently, we'll use the depth first search technique to gather the information about the tree structure. Then we'll compute some values to make handling each query faster. Okay, each query is independent, so the tree resets after each one. Okay, now let's walk through the code. Here we have the class solution and a function defined tree queries. Here root of the tree is passed and the queries list is also passed. We have to return another list as output. Okay, so first of all I'm going to initialize arrays to store various information about the nodes. Okay, I'm taking heights as a variable, an array. I'm initializing it with 0 and some number like 50,000 I'm taking. Okay, this is going to be the heights of leaf nodes. Then I'm taking another variable d, which is used to store the depth of each node from the root. So I'm initializing it at 0 again. I'm initializing like this. Then I have another variable L and also taking another variable R. Okay. First of all, let me initialize L. L with same 1 0 0 0 and 1. I'm taking another variable R, initializing with 0 again, multiplied by 1. Right. These L and R used to track the range of leaf nodes under each node's subtree. This helps us efficiently calculate the maximum heights excluding the certain subtrees. Okay. Then I'm taking another variable called length of leaves, which is initialized to 0. This is a counter to keep track of the total number of leaf nodes as we explore the tree. Okay. Then I am going to initialize a function called search. Okay, in this search what we are passing, I'm initializing the function called search. I'm passing p, which is the tree node. Then I'm passing a variable h, height, it is an integer. Okay, what we are going to return, none. Okay, so I'm taking a non-local variable length leaves because we already have the length leaves, so it is a initialized as non-local because this is okay. Then I'm taking d of p dot val, which is equals to current node's depth, that is I'm initializing with it's with the height. Okay, this search function I'm writing this because it basically performs the depth first search to gather the essential information. Okay, now we have to check if the leaf node found or not. Okay, for that, if not p dot left and not p dot right, in this case what we have to do, heights of length leaves will be equal to h. This is used to store leaf height. Okay. Next, L of p dot val is equals to R of p dot val, which is equals to length of leaves. This both indices are same for the leaf node. Okay. Now we have to increment the length of leaves by 1 and then just return. That's it. Now if the above condition fails, if leaf node is not found, then L of p dot val is equals to length of leaves. This is to store left index for the current node. Okay, then we have to recursively process left and right subtrees. Okay, if p dot left, then we are recursively processing search of p dot left and h plus 1. Okay, then if p dot right, in this case we also have the recursive function again, p dot right and h plus 1, sorry there is a typo, h plus 1. Then r, we are updating this with p dot val equals to length of leaves minus 1. Okay, I'll explain. Basically this function we are using to perform the depth first search, and d dot p val, this line d dot p val, sorry, d of p dot val equals to h. This records the depth of each node. When we find a leaf node, we store its height in heights. Okay, and since it's a leaf, L and R will have the same index. Okay, L and R will have the same index. For each non-leaf node, we set L of p dot val equals to, and before exploring its children, and R of p dot val afterward. This way we know the range of leaf nodes within each subtree. Okay, this function helps us efficiently identify and store information about the all the nodes which we will use later when processing the queries. Okay, so we have completed our search function. We have to exit that. I'm just calling the search function here, passing the root and 0. Okay, now I'm taking a variable n equals to and initializing with length of leaves. This is the total number of leaf nodes here. And I'm taking a variable max L, max underscore L equals to 0. It is times n. This will store the maximum heights from left, and I'm taking another variable max underscore R. I'm doing the same thing, initializing it with 0 times n. This will store the max heights from the right. Now we have to build a prefix and a suffix minimum subarrays. Okay, so for that I'm taking for I in range of 1 and n, max underscore L of I will be equals to max underscore L of I minus 1 and heights of I minus 1. Okay, the same thing we have to do with the right side, right? Max R of n minus I minus 1 equals to max underscore R of n minus I and heights of n minus I. This is to store the max height from the right. I'll explain what we have done here. Once we completed our initial traversal of the tree, we know how many leaf nodes will be stored in this variable called n. Okay. Next, we have initialized two arrays max underscore L and max underscore R to store the maximum heights from the left and right directions across all the leaf nodes. These arrays are built in such a way that max underscore L of I will hold the maximum height from the start up to leaf I, and max R holds the max height from the end up to the leaf I. This computation will allow us to quickly find the maximum height on either side of nodes subtree during the each query. Okay, next we have to exit the loop. Then I am taking a variable called result. I'm making it as an empty list. Okay, now I'm taking another for loop for query in queries. We have to process the each query now, right? Queries. Now we have to find the maximum height excluding the current nodes subtree. Okay, so I'm taking a max L equals to max underscore L of query. Okay, this will give us the max height to the left. I'm taking another variable max R equals to max underscore R of query. This will give the height to the right. Now result is max of maximum left height and maximum right height and current depth minus 1. Okay, so res dot append what we are doing, max of max L and max R comma d of query minus 1. Okay, I'll explain what we have done in this loop. We have a prefix and suffix maximum subarrays ready, right? Then we can efficiently answer each query. For each query, we'll identify the left and right bounds for leaf nodes affected by that query using the L query and R query. Using the max L and max R, we'll quickly find the maximum heights from both left and right sides, excluding the subtree of the queried node. Finally, we'll calculate the height as the maximum between these values and dquery minus 1, since height needs to be account for the removal of the subtree. Okay. Next, what we have to do? We have to return the list, right? Return the result. Okay. Now let's run the code and check. Yes, our test cases are being passed. Let me submit the code and check if all other test cases will be passed or not. Yes, as you can see here, our code perfectly works and we have a runtime of 163 milliseconds and it also beats 100% of the users on LeetCode. And that's it. We have successfully solved the problem by breaking it down into pre-computing necessary values and efficiently handling each query. By storing the heights and depths and using prefix and suffix arrays, we made our solution highly efficient. I hope you found this video helpful. And if you feel that, please do subscribe our channel CodeStreak Daily and do hit the notification bell icon so that you do not miss any update on our channel. And if you want to keep maintaining a streak on both Geeks for Geeks and also on LeetCode, please do subscribe our channel. And if you like this video, hit the like button and also share it with your friends. See you in the next video, guys. Until then, keep streaking.